For 50 years, humanity has basically been, stuck in the shallow end of the cosmic pool, low Earth orbit.
Right, just circling the block.
Exactly. But now, NASA is finally packing its bags for deep space. But, the plan to get us there? It involves 400-foot commercial rockets, deep space gas stations, and a price tag in the billions. Welcome to the debate.
It's a massive undertaking.
It really is. Today, we're looking at the Artemis program. This is NASA's monumental initiative to return humans to the moon. And the central question before us is this. Is NASA's highly complex, multi-partner architecture the definitive, sustainable blueprint for making humanity a multi-planetary species? Or is it a precarious, overloaded system driven by political constraints rather than true exploration efficiency?
And that is exactly where we divide. Right, so I take the position that the Artemis architecture, utilizing the Space Launch System, the Orion spacecraft, and the Lunar Gateway, is a brilliantly robust foundation that is absolutely necessary for our deep space future.
And I take the contrasting view. While returning to the moon is, an inspiring goal, the current architectural plan is a Frankenstein of delayed legacy technology and unproven commercial elements. It's a system that risks collapsing under its own complexity, and in doing so, potentially costing America the new space race.
Well, to really understand why we built Artemis this way, we have to look back at Apollo. Artemis is named after Apollo's twin sister in Greek mythology, and it's meant to be the sustainable successor.
The key word being sustainable. Right. Apollo was a magnificent sprint. I mean, we proved we could land, we proved we could beat the Soviets. But that sprint ended in 1972 precisely because it wasn't designed to last. It was a flag and footprints mission.
Yeah, get in, get out.
Exactly. Artemis is fundamentally different. It's not a sprint. It's designed to establish a permanent human presence.
But what does permanent presence actually mean in this context? Because when you look at the immediate milestones, we are essentially starting from scratch.
How so?
Well, we haven't left low Earth orbit with a crewed vehicle since Gene Cernan stepped off the moon. We are relearning how to walk here.
We are starting fresh, sure, but we're starting with a much bigger vision. Take the imminent Artemis 2 mission. We're sending 4 astronauts on a 10-day lunar flyby, taking them further than any humans have ever traveled.
It's a huge test of the life support systems. It is, and we're talking about the Artemis generation here. A crew that includes the first woman and first person of color to go to deep space. But beyond the inspiration, going back to the moon is scientifically and practically essential.
Right, the South Pole craters.
Yes, the undisturbed craters at the lunar South Pole offer a 3.5 billion-year-old record of the solar system. But more importantly, those permanently shadowed craters contain water ice.
Which is the holy grail for space exploration.
Exactly. Water means life support for astronauts to drink and breathe, but it also means rocket fuel. If you can separate water into hydrogen and oxygen, you have propellant.
Meaning we don't have to carry it all from Earth.
Precisely. That ice is the literal springboard to Mars. It means we don't have to drag all our fuel out of Earth's heavy gravity well. The entire Artemis architecture is built to harvest that potential and create a sustainable economy in deep space.
I come at it from a different way. I acknowledge the romantic appeal, and yes, the scientific value of those 3.5 billion-year-old craters is undeniable.
It's massive.
It is. But we have to pivot from the romance of exploration to the mechanical and logistical realities of how NASA actually plans to pull this off. When you strip away the branding, the Artemis architecture is fundamentally overloaded with firsts.
Every space program is full of firsts. That's the nature of exploration. I mean, we didn't know how to do an orbital rendezvous before Gemini either.
True, but let's look at the foundational piece of this specific architecture, the Space Launch System, or SLS rocket. This is a vehicle that costs roughly $800 million per launch.
It's a heavy lift vehicle. It's going to be expensive.
But because of that astronomical cost, it flies incredibly rarely. Historically, we're looking at once every 3 years. That low flight cadence is a massive operational risk.
You're saying they don't get enough practice.
Precisely. During the Apollo era, Saturn V launches were happening just a couple of months apart. That steady cadence built muscle memory for the engineers, the ground crews, and the astronauts. With SLS flying so infrequently, the workforce simply cannot build that operational rhythm?
I think they have plenty of simulation time.
Simulations aren't flight hardware. Furthermore, the Aerospace Safety Advisory Panel, which is an independent oversight group, recently raised severe concerns that the original Artemis 3 direct landing plan was so inherently risky it had to be reprofiled.
They adjusted the mission profile, yes.
They're now looking at an Earth orbit rendezvous to test systems first rather than going straight to the moon. This constant shifting of the baseline architecture proves that this complexity threatens the overarching goal.
See, I'm not convinced by that line of reasoning because you're fundamentally underestimating the sheer capability of the hardware we have actually developed.
Go on.
Let's look at the SLS itself. Sitting on the pad, it weighs over 6 million pounds and generates 8.8 million pounds of thrust. That is 15% more powerful than the monster Saturn V rocket.
It's a beast, I'll give you that.
And it achieves this using 4 RS-25 engines. These are derived from the Space Shuttle program, meaning they are some of the most reliable, thoroughly tested engines in human history.
Wait, that power is impressive. But at what cost? You're talking about bolting together legacy hardware, shuttle engines, that were originally designed to be reusable and throwing them into the ocean after a single flight?
Well, they're updated versions. It's wildly inefficient. We are discarding perfectly good, historically reusable engines.
It's a pragmatic use of proven technology to get a massive payload safely off the Earth. And paired with the SLS is the Orion capsule, the crew vehicle. Orion is a massive leap forward from Apollo.
In terms of volume, sure.
Right. It's 33% larger, so it can comfortably support 4 astronauts instead of 3. It uses advanced solar power arrays from the European Service Module rather than Apollo's limiting battery power. Artemis 1 proved this rocket can fly, and fly beautifully.
It flew, yes, but I wouldn't call it a flawless proof of concept, especially when we talk about Orion's readiness for human passengers. Consider the heat shield.
The charring issue, you mean?
Exactly. During the Artemis 1 uncrewed test flight, Orion came screaming back into the Earth's atmosphere at 32 times the speed of sound. The heat shield has to withstand temperatures of 5,000 degrees Fahrenheit.
It's an extreme environment.
Just to put that in perspective, that is half the temperature of the surface of the sun. To bleed off that incredible speed, NASA used a skip re-entry maneuver.
Which is a brilliant piece of engineering. It's essentially bouncing the spacecraft off the upper atmosphere like skipping a stone across a pond.
Right, to slow it down?
Exactly. You dip in, let the friction of the atmosphere slow you down and absorb some of that kinetic energy. Then you pop back up into space to let the spacecraft cool off for a few minutes. And then you dip back in for the final descent. It prevents the heat shield from taking all that 5,000-degree punishment at once.
In theory, it's brilliant. But in practice, engineers discovered an unexpected, charred layer of the heat shield where chunks of the ablative material had actually come off during that re-entry.
It was anomalous, but
We cannot casually brush past that. When a spacecraft re-enters the atmosphere, that friction isn't just a minor hurdle, it's a plasma inferno. The Space Shuttle Columbia disaster in 2003 was caused by damage to the thermal protection system.
which is exactly why we test.
When you have humans on board, unexpected charring is a massive red flag. It points to the inherent danger of rushing a complex, bespoke vehicle into service.
I see why you think that, but let me give you a different perspective. Engineering is about finding limits during testing so you can correct them before crewed flights.
But the material physically chunked off.
They flew Artemis 1 uncrewed precisely to stress test that heat shield. Identifying the root cause of the charring and fixing it is the system working exactly as intended. But where the true genius of Orion lies isn't just in surviving re-entry, it's in the physics of the journey itself. The orbital mechanics of Artemis are a masterclass in efficiency.
You're talking about the deep space trajectories?
Yes, Apollo was essentially a 6-day direct sprint to the moon. They had to do it that way because the small command module only had about 14 days of life support.
Artemis utilizes incredibly sophisticated orbital pathways to maximize time and space while minimizing fuel.
Using the gravity assists.
Right. Artemis 2 will use a free return trajectory. By carefully targeting a specific point in space, the gravity of the Earth and the Moon will naturally sling the spacecraft back home without requiring the main engines to fire. It's the exact physics that saved the Apollo 13 crew.
And for the later missions, they're using distant retrograde orbits.
Exactly. By flying opposite to the Moon's travel and balancing the gravitational pull of the Earth and the Moon, Orion requires almost zero fuel to maintain its orbit. And to get into those orbits, they use the Oberth effect. Explain how that actually works in practice, because to a lot of people it sounds like free energy.
It's not free energy, but it is a brilliant manipulation of kinetic energy. Think of it like riding a bicycle down a steep hill. If you pedal hard right at the very bottom of the valley, when you're already going your absolute fastest, that energy translates into way more speed to get you up the next hill than if you had pedaled at the top.
So they burn the engines at the closest approach?
Yes. By firing its engines at the closest approach to the Moon, deepest in its gravity well, Orion maximizes its velocity, or delta V. It saves massive amounts of fuel, allowing the spacecraft to stay in deep space for weeks to test radiation shelters and life support systems.
I will grant you that. The orbital mechanics are elegant. The physics of the free return trajectory and the Oberth effect are undeniably brilliant.
It's incredible math.
But my issue is not with Isaac Newton. My issue is with the physical architecture required to actually set foot on the lunar surface. Because here is the glaring flaw in everything you just praised. Orion cannot land on the Moon.
It was never designed to. It's strictly an orbital vehicle.
Exactly. To actually get astronauts to the lunar South Pole, Orion must dock with a human landing system, or HLS. And what is NASA relying on for that? SpaceX's Starship. Let's break down the sheer absurdity of the logistics involved here.
I wouldn't call it absurd.
Starship is a 400-foot-tall mega rocket. It's not a nimble little lunar module like Apollo had. To get a lunar variant of Starship to the Moon, SpaceX has to confront the tyranny of the rocket equation.
Meaning a rocket burns most of its fuel just escaping Earth's gravity, leaving almost nothing for the actual trip to the Moon unless it tops off in space.
Right, so to solve that, SpaceX first has to launch a massive propellant depot into low Earth orbit. Then they have to launch roughly 15 separate Starship tanker flights just to refuel that depot in space.
It's a lot of flights, yes.
Then the actual lunar Starship launches, docks with the depot, takes on the cryogenic liquid oxygen and liquid methane, and only then can it head to the Moon to wait for Orion.
It's a distributed launch architecture.
It's a logistical nightmare. You are talking about coordinating over a dozen flawless mega rocket launches in rapid succession just to make one single lunar landing possible. And the fluid transfer itself, moving super-chilled cryogenic liquids in zero gravity, isn't like pumping gas at a station on Earth.
No, obviously not.
In space, liquid methane and oxygen don't just sit nicely at the bottom of a tank. Without gravity, they cling to the walls, they float in blobs. And more importantly, space involves extreme temperature swings. If the sun hits the tank, the cryogenic liquid boils off and turns into gas.
Which they manage with insulation and venting.
You have to vent it or the tank explodes. So you are racing against time trying to pump super-chilled liquids between two massive vehicles before the fuel literally evaporates into the vacuum of space. No one has ever demonstrated cryogenic fluid transfer at this scale in orbital conditions. The risk of a cascading failure in that launch chain is astronomically high.
You can call it a logistical nightmare if you want, but the complexity you're discussing is exactly why NASA has shifted to a model of pre-staging.
Pre-staging just stretches the risk out over more launches.
Yes, it requires multiple launches, but let's look at the alternative. If NASA tried to launch the entire mission, the crew capsule, the transit habitat, and a lander capable of reaching the South Pole on a single rocket, that rocket would have to be impossibly large.
Or you build a smaller lander.
But by having commercial partners like SpaceX and Blue Origin handle the landing system separately, NASA doesn't have to carry the dead weight of a lander all the way from Earth on a single rocket like they did with Apollo.
But you're trading vehicle mass for mission complexity.
We're trading a single point of failure for a modular, sustainable system. And this ties into the most crucial piece of the Artemis architecture, the Lunar Gateway. The Gateway is a space station that will be placed in a near-rectilian halo orbit around the Moon.
For our listeners, let's clarify what that actually means, because it's not a traditional circular orbit.
Good point. Think of the Earth and the Moon like two magnets pulling on a metal ball. There's a specific oval-shaped path around the moon where the gravitational pull of the Earth perfectly balances the pull of the moon.
Right. The Lagrange points are involved there.
Exactly. That's the halo orbit. Because it sits in that perfect gravitational sweet spot, the Gateway requires almost zero fuel to stay put. But more importantly, from that unique orbit, the Gateway can adjust its position to allow landers access to the entire lunar surface, including the critical South Pole.
Whereas Apollo was restricted.
Apollo could never do that. They were restricted to equatorial landing sites because of their fixed orbital plane. Gateway is an open standard hub. It allows commercial landers to be pre-positioned. Orion arrives, docks at the Gateway, the astronauts transfer to the lander, and head down. It makes the moon a fully accessible, long-term destination.
I'm sorry, but I just don't buy that. Let me tell you why. If the Gateway and the Starship integration plan were as robust and seamless as you claim, NASA wouldn't be drastically pulling back on their immediate goals.
What do you mean pulling back?
Look at the recent mission reprofiling. NASA is now standardizing the SLS to what they call a near Block 1 configuration. They are practically abandoning the rapid evolution of the upper stage of the rocket because it's too complex to manage alongside everything else.
That's a supply chain decision.
And look at the Artemis 3 mission profile. Originally, it was supposed to be the grand return to the lunar surface. Now, to reduce risk, they are planning to move the Artemis 3 rendezvous to low Earth orbit instead of lunar orbit.
To test the systems first.
But why are they testing them in Earth orbit? Because performing the first integrated docking, crew transfer, and system checkout between an Orion capsule and a 400-foot commercial lander 250,000 miles from Earth is incredibly dangerous.
Well, obviously.
Doing it in Earth orbit provides immediate abort options and easier communication. I agree with the safety choice, but this scale-back fundamentally proves that the original Gateway and Starship integration plan was dangerously overambitious. The architecture is dictating the mission rather than the mission dictating the architecture.
That's an interesting point, though I would frame it differently. Testing a massively complex docking maneuver in low Earth orbit before committing to deep space isn't a sign of failure. It is the definition of a mature, safety-driven engineering culture.
It's a delay.
And as we're standardizing the SLS rocket, as NASA Administrator Jared Isaacman pointed out, that is actually solving the flight cadence issue you brought up earlier.
How does freezing the rocket design solve the fact that it only flies every 3 years?
Because if you stop redesigning the rocket every few flights, you can accelerate manufacturing. You pull hardware forward on the assembly line. You bring launches from 1 every 3 years to 1 every 10 months.
In theory.
That repetition builds the very muscle memory you claimed we were lacking. And by partnering with commercial entities like SpaceX and Blue Origin, we are subsidizing the creation of a robust civilian and commercial space workforce. This methodical, commercial-heavy approach is exactly what will secure American leadership in space for the next century.
That assumes we have a century to secure it. But all these delays with commercial landers aren't happening in a vacuum. Every month we spend testing refueling in low Earth orbit is a month our global competitors use to close the gap.
You're bringing in the geopolitical angle.
Let's introduce the geopolitical reality here. The space race of the 1960s was against the Soviet Union, and it was a sprint driven by the Cold War. The space race today is against China, and the stakes are arguably higher because it's about permanent strategic positioning.
You're talking about the lunar South Pole specifically.
Exactly. China already has a robotic base on the moon. They have stated their explicit intention to land taikonauts on the lunar surface by 2030. They are moving with singular state-funded focus.
But they have their own technical hurdles.
Sure, but they aren't waiting for a commercial partner to figure out zero-gravity cryogenic fluid transfer. If America's return to the moon is bogged down by delayed Starship tanker flights, or if SLS suffers another helium pressurization issue during testing and takes months to roll back to the vehicle assembly building, our timeline slips.
And you believe that hands the advantage over entirely.
If our timeline slips past 2030, China will reach the lunar South Pole first. They will claim the strategic high ground, they will secure the best access to those water ice resources while we are still trying to coordinate 15 commercial tanker flights in Earth orbit. The complexity of our architecture is a strategic vulnerability.
I understand the urgency, but I disagree with the premise because it treats the moon like a finish line rather than a foundation. The goal isn't just to plant a flag at the South Pole before 2030 just to say we beat China. If that were the goal, we would have built a direct descent Apollo clone. We know how to do that.
But at least we would be there.
But for how long? As Harrison Schmitt, the Apollo 17 geologist, pointed out, human evolution in the universe has begun. We are going to the moon to arrive with the infrastructure to stay permanently.
It's a very long-term view.
We aren't just bringing a flag. We are bringing commercial landers, the Lunar Terrain Vehicle, an unpressurized rover so astronauts can navigate miles of the surface in their spacesuits, and we're laying the groundwork for lunar surface nuclear reactors to generate continuous power during the freezing 14-day lunar night.
It's a beautiful vision of a lunar city.
It's designed for permanence. We don't have to make a binary decision between the moon and Mars. As Administrator Isaacman noted, we can parallel these efforts. The Gateway's halo orbit is specifically designed to perfect the docking and life support maneuvers we will need for a Mars transit vehicle.
Assuming the Gateway gets built on time.
We are building a deep space logistics chain. China may touch down, but the Artemis architecture ensures that when America and its international partners arrive, we possess the capability to live, work, and eventually launch humanity to Mars directly from the lunar surface.
That's a compelling argument, but have you considered that a logistics chain is only as strong as its weakest link? You mentioned the international partners, the European service module powering Orion, the Canadian robotic arms on Gateway, the Japanese contributions to the rovers. It is a beautiful vision of global cooperation.
It really is.
But integrating hardware built across different continents, managed by different space agencies, and launched by competing commercial companies creates a massive matrix of failure points.
It distributes the cost and the operational load.
It also distributes the risk, compounding it. If Blue Origin's Blue Moon lander faces manufacturing delays, or if SpaceX's Starship continues to have issues with its massive orbital fueling operations, the entire Artemis timeline grinds to a halt.
That's a lot of ifs.
The astronauts sitting in the Orion capsule cannot land on their own. They are completely dependent on an incredibly fragile chain of events happening perfectly, sequentially, and on time. We're trading the robust, self-contained mission profile of Apollo for a sprawling, decentralized network that has never been tested in deep space. It is a precarious balancing act.
Well, a precarious balancing act to some is a synchronized symphony to others. Let's summarize where we stand. I maintain that the Artemis program's complex network, the sheer power of the Space Launch System, the deep space resilience of the Orion spacecraft, the innovative pre-staging of commercial landers, and the open hub concept of the Lunar Gateway is the exact sustainable framework required today.
Right. It finally moves us away from disposable, single-use sprints. It builds the actual, reusable infrastructure necessary to transform humanity into a multi-planetary species. And I maintain that while the goal of establishing a permanent lunar presence is a noble and necessary one, the current architecture is dangerously over-engineered. It is a labyrinth of untested cryogenic refueling logistics, low flight cadences, and shifting mission profiles. By relying so heavily on a chain of commercial and international dependencies, we leave the door wide open for global competitors with simpler, more direct architectures to claim the lunar South Pole first.
Despite our distinct views on the architecture, I think we both agree that the stakes for humanity could not be higher. Returning to the moon after an absence of more than 50 years to test deep space habitats and life support is, without hyperbole, the greatest adventure in human history.
Absolutely. The Artemis generation is about to witness space exploration shift from grainy history books back into a living, breathing legacy. When those 4 astronauts on Artemis 2 fly around the far side of the moon, observing parts of the lunar surface never before seen by human eyes, it will fundamentally change how an entire generation looks up at the night sky.
It is a profound shift in our relationship with the cosmos. It forces us to look up and realize we aren't just earthbound anymore. So as we look toward the upcoming launches, we leave it to you, our listeners, to consider. Is NASA's ambitious, distributed infrastructure a masterstroke of sustainable exploration, or a logistical labyrinth that might trip us up before we even arrive?
Time will tell.
The fiery ascent of the Space Launch System and the upcoming missions will ultimately provide the answer. But one thing is certain, after 50 years of confining ourselves to low Earth orbit, Humanity is finally stepping out into the dark again. We'll see you next time on The Debate.